Solar power forecasting represents the systematic prediction of future electrical output from photovoltaic (PV) systems across defined time horizons, transforming solar energy from an inherently intermittent resource into a dispatchable, manageable asset. This predictive capability has become indispensable in modern energy systems as solar installations proliferate worldwide. At its core, solar forecasting estimates electricity generation by analyzing multiple interconnected factors: solar irradiance in its various forms, direct normal irradiance, diffuse horizontal irradiance, and reflected irradiance, atmospheric conditions including cloud cover dynamics, aerosol concentrations, and humidity levels, system-specific characteristics such as panel orientation angles, conversion efficiency, and performance degradation over time, and environmental conditions including temperature effects and shading impacts from surrounding structures or vegetation. Beyond mere generation prediction, contemporary forecasting serves as a critical control and optimization input that enables sophisticated energy management decisions. It allows operators to adjust battery charge and discharge schedules proactively, align household or commercial loads with anticipated solar availability, minimize PV curtailment, which represents wasted clean energy generation potential, and optimize grid interaction including import and export decisions. Without accurate forecasting, system operators must rely on conservative assumptions that inevitably lead to excess reserve capacity, inefficient battery utilization, and increased solar curtailment, all of which undermine the economic and environmental benefits of solar energy. The importance of solar power forecasting cannot be overstated in today's energy landscape. Solar energy's inherent intermittency poses significant challenges for grid operators and energy system managers. Cloud cover can change rapidly, causing steep power ramps that are difficult to anticipate and manage without reliable predictive capabilities. These rapid changes constrain grid infrastructure, require excessive reserve capacity to maintain stability, and lead to missed opportunities for optimal solar utilization. Accurate forecasting enables anticipatory control, allowing energy systems to act before variability manifests rather than reacting to it after the fact. This proactive approach is particularly valuable in energy management systems, EMS, where solar forecasts serve as a core decision variable. Within advanced EMS platforms, forecasts enable battery charging during periods when excess PV generation is expected, load shifting toward periods of high solar availability, and reduced grid imports during high-price electricity periods. When combined with time of use, tariffs or dynamic pricing structures, forecasting directly translates into significant cost savings and emissions reductions. For grid operators and market participants, forecasts support critical functions including unit commitment and dispatch decisions, reduction of balancing costs and reserve requirements, and improved accuracy of renewable energy market participation, ultimately contributing to both grid reliability and market efficiency. Methodological approaches to solar forecasting. All solar forecasting techniques ultimately derive from three methodological foundations: physical methods, statistical methods, and holistic integrated approaches. Physical forecasting methods model the physics of the atmosphere and solar radiation to predict irradiance and resulting PV output. These approaches leverage sophisticated numerical weather prediction (NWP) models, satellite imagery that captures cloud motion and cloud optical depth, ground-based sky cameras for localized cloud tracking, and fundamental solar geometry calculations combined with atmospheric transmittance models. The primary strength of physical methods lies in their strong theoretical basis and their effectiveness for medium and long-term forecast horizons. They are highly scalable across large geographic areas and provide robust predictions when atmospheric conditions are relatively stable. However, physical methods have notable limitations. They demonstrate lower accuracy for very short-term forecasts where cloud dynamics evolve more rapidly than model update cycles can capture. They are sensitive to errors in cloud modeling including cloud height, thickness, and motion predictions, and they require substantial computational resources, making them relatively expensive to implement and operate. Despite these limitations, physical methods remain the backbone of medium to long-term solar forecasting, particularly when enhanced with statistical post-processing techniques. Statistical forecasting methods infer future generation from historical and real-time PV output data, often serving to correct or refine outputs from physical models. Common techniques within this category include persistence forecasting, the simplest but often highly effective approach for very short time horizons, regression models that establish mathematical relationships between input variables and PV output, time series analysis techniques that identify patterns in historical data, and machine learning models when trained using statistical approaches. Persistence forecasting operates on the fundamental assumption that near-future solar output equals current output, which may appear simplistic but proves highly effective for very short horizons, typically minutes, and serves as a widely used benchmark model against which more complex methods are evaluated. The strengths of statistical methods include their speed of execution, their data-driven nature that allows them to learn from actual performance, and their high accuracy in stable weather conditions where patterns are consistent. However, statistical methods exhibit significant weaknesses. They perform poorly during rapid weather changes where historical patterns no longer apply. They have limited extrapolation capability when confronted with novel conditions outside their training data, and they typically require substantial historical data for effective training and may struggle with new installations where such data is unavailable. These limitations have driven the development of more sophisticated approaches that combine physical and statistical methodologies. Holistic and integrated forecasting methods represent the most advanced approach to solar power forecasting, combining physical weather models, statistical corrections, real-time asset performance data, and market and tariff information within a forecast-driven energy management system. This integration treats the entire energy system as a closed-loop optimization problem that is continuously updated in real time. Typical EMS inputs include rooftop PV production data, battery state of charge and degradation models, household or industrial load profiles, electricity prices and grid constraints, and both weather forecasts and nowcasts. The decision outputs from this integrated approach include optimized battery charging and discharging schedules, grid import and export timing recommendations, load prioritization strategies, and curtailment avoidance tactics. This holistic approach acknowledges that solar forecasting cannot exist in isolation. Rather, it must be actionable intelligence embedded within a broader energy management framework.